Okay, so it's my pleasure to introduce our chair this morning, Michael McGuire here from Oak Ridge National Laboratory. Michael will introduce himself and then our speakers this morning.
Thanks, Travis. Good morning, everyone. Uh, as Travis said, I'm Michael McGuire. I'm in the Material Science and Technology Division here at Oak Ridge, where I lead the Correlated Electron Materials Group. We're an experimental condensed matter physics and materials development group focusing on crystal growth, characterization, and neutron scattering from magnetic, superconducting, 2D materials, things like that. I'm also the thrust lead for the materials research in the Quantum Science Center, where we're focusing on developing topological superconductors and quantum spin liquids, among other things. And that's what we're going to hear a lot about in this morning's sessions. So I want to just go ahead and hand it over to our first speaker, Vivien Zapf from the National High Magnetic Field Lab at Los Alamos, who's also the deputy director for the Quantum Science Center. So take it away, Vivien.
All right, thank you, Michael. So this is your first introductory talk, but it's on Thursday for shuffling reasons. So you're getting it a few days delayed from where it was supposed to be, but that's okay. So I'm going to try and give you an overview of the Quantum Science Center a little bit, but also the broader landscape, the different approaches to qubits, and where we fit in this. Okay. So any slide like this that I show you will immediately be out of date as soon as I show it, and was already out of date as when it was made, but it gives you a slightly out of date snapshot. So basically a lot of countries are investing a whole lot of money. Some of the numbers are actually too small. The US is investing more than this because this is the quantum initiative, and we fund quantum through other routes as well. But the point is there's lots of people interested in this subject. Okay, and this is also, out of date, but gives you some idea that, this investment is motivated by tremendous progress. So this is an exponential increase in the qubit coherence time. This focuses on superconducting and photonic qubits specifically, but it shows you that, there were 5 orders of magnitude improvement from 2000 to 2020, which is driving a lot of the excitement. Over on the right, this is a picture. This is from our colleague Aaron Cho, but this basically shows if this is the surface area is meant to indicate the number of qubits that the number of physical qubits that people are currently implementing. This is where we want to be to start thinking about practical gate-based quantum computing. This is where we need to be for the dark matter sensing effort. So we have a ways to go in scaling up the number of qubits that we can simultaneously implement and address in one system. Okay. So the National Quantum Initiative is what's funding the Quantum Science Center and the other centers. It's now in its we're in our 4th year. So it was signed into law in 2018. The money went out in 2020. There are a whole bunch of different centers that were created, funded mostly by the Department of Energy, the National Science Foundation, and then also under the NDAA, money was given to these other labs. So here in red is the Quantum Science Center, which is organizing this school. So this school goes, between these 5 centers. Next year, it'll be QSA organizing it. So you will probably notice there's, for example, a little bit of a topological bent to the classes, because that's one of our focuses. And then each center has a different focus. So the school changes with each year. So the Quantum Science Center has, as many such things do, 3 thrusts. So there's sort of you could call this a materials thrust, although it includes also theory, where we're trying to develop new approaches to quantum computing, specifically focusing on topology. And in fact, Michael McGuire leads this thrust. And then we have an algorithms thrust that's looking at, as you've already heard, many of the different challenges, improving the algorithms, improving error mitigation, and sort of addressing most of the different hardwares. And then we have a sensing thrust, which a big piece of this is trying to sense dark matter. Turns out that superconducting qubits are one of the leading sensors that people are using to try and find dark matter. But of course, we need to improve their resistance to cosmic rays and scale them up to larger numbers. But also there's focus here on different kinds of sensing techniques for materials, and also there's work on single photon emitters, so it's pretty broad. Okay. This slide, also out of date and stolen, shows you the different approaches to quantum computing, where the ones in gray are where the Quantum Science Center is putting some more significant effort. So we have approaches based on atoms, such as trapped ions and cold atoms. It's also, of course, molecules and other things coming off that. Quantum annealing is not so much a hardware approach as a different software approach, perhaps focusing on Ising spins. And then, of course, we have the superconducting qubits and all their variety, with transmons being, out at the front. Silicon based spin qubits. Molecules are very much in the basic research, so there are no companies, but a lot of basic investment. Semiconducting defects. These are more on sensing, less on quantum computing, but there's some effort. And then, of course, topology is where we're focusing, and then photons. So I'm going to go in a little bit of not a huge amount of depth, but I'll talk a little bit more about each one. Okay, but first let me finish my introduction to the Quantum Science Center. So these are our different institutions in the Quantum Science Center. So we have about 240 researchers from 4 national labs, 3 industries, and 9 universities. Actually, that's probably out of date by now. We just added UC San Diego. This is an attempt to show that we all work together. So each of these lines is a a cross collaboration across the different institutions within the Quantum Science Center. And then our technology transfer partners are Microsoft, Cold Quanta, now Inflection, and IBM. So with each of these, we have a project that goes a little bit beyond just using their hardware, and in terms of a development collaboration. So for example, with Microsoft, we are of course working on topological materials and trying to learn from them the more devicey aspects of it. Also, we're contributing to the quantum intermediate representation, so Q# language. And then with Cold Quanta, there's a whole bunch of sort of basic science collaboration with them to see what we can do with cold atoms to improve our understanding of condensed matter and cold atom systems, and also working with them to improve their hardware for their next generation. And then finally with IBM, there's some collaborations on error mitigation and also on testing their hardware for quantum simulations. Okay, questions so far on that extremely high level overview of what the Quantum Science Center is focusing on. So we are in our 4th year out of 5, and we hope out of 10. So right now, the National Quantum Initiative Reauthorization Act is in various houses and subcommittees of Congress. And so last November, the House Science Committee enthusiastically recommended that we get another 5 years of the National Quantum Initiative. And they, laid out things they wanted to see funding, including more funding for the Quantum Science Center and the other centers. And right now, the House Appropriations Committee is thinking about it, and they came out with a draft, which also suggests either flat or possibly increased funding for the DOE centers. It calls for a quantum roadmap, whatever that is. So they want to see where this is all going in the future, and how maybe what they want to know is how many more years do they have to fund this for. But certainly this seems hopeful. So if our government actually agrees on something in the near future, we might have 5 more years of funding for the National Quantum Initiative Act, and that would allow these centers to continue. So certainly we have a lot of work left to do. Okay, so where is quantum computing? So this is probably another one of those impossible slides that is out of date the minute you write it, and hard to summarize. But I mean, roughly, if looking at this from the point of view of a condensed matter scientist, and wanting to use quantum computers to do practical physics problems, what I see is that right now there's some low-hanging fruit. We can simulate simple systems, especially magnetic spins and some nuclear systems, especially if you restrict yourself to the Ising spins. So D-wave, Q-era, other sort of quantum annealing approaches are now, demonstrating that they can simulate things better than we could by other theoretical methods. So that has arrived. So I'll call that the low-hanging fruit. What we're trying to do is go beyond Ising spins to Heisenberg spins or XY spins, and also simulate systems. So this is sort of starting to become practical. And then ultimately we need to scale up to look at, the really big condensed matter problems, correlated electron systems, chemical systems, high energy physics, what happens in the nucleus of an atom. This is going to require not just Ising spins, and it's going to require scaling to larger numbers and to better fidelities. So this is the near-term hope. And then, of course, ultimately, we want general purpose gate-based quantum computers. And this is a ways to go. The bottlenecks, of course, are the decoherence, the loss of quantum information out of each qubit, the gate fidelity problems. So if you ignore error correction, we have to go all the way from where we are now, somewhere in the maybe 99.9% gate fidelity up to here. Or can we bring in fault tolerant computing and bring down that requirement? So depending on who you talk to, maybe we need 4 nines, maybe we need 5 nines. And then, of course, the cost is you need a whole lot more qubits to create logical qubits that are error corrected. So this is where we need to go. And I don't think anybody can put a number of years on this right now, but definitely what we're seeing is progress. So yeah. All right. So you heard from John Preskel about the, this is his slide, the approaches to quantum computing that are currently, I would say, implemented, where you can, in most cases, maybe go on their website and download some software and maybe test their hardware. So there's superconducting qubits. This is 2 different things, trapped atoms and, cold atoms and trapped ions. Silicon is sort of getting there, and photonics is sort of getting there, trying to catch up with the other 2. But I want to show you another slide that has a whole lot more. So those are the approaches that kind of leapt ahead in the beginning of this race, in large part because there was a lot of previous research on these. I mean, there's decades of previous research on many of these approaches that got us to where we are now. And so, you could say that trapped ions, cold atoms, transmons are in the lead. So I'm going to call these little rabbits. But although they're in the lead, we have a ways to go. So they're, flirting with maybe 99.9% gate fidelities, and we need to be at least another order of magnitude out, and we need to scale several orders of magnitude. So here's our noise decoherence scaling wall that we have to climb. And then there's some that are sort of coming up from behind. There's the photons, the spins, and semiconducting quantum dots that are not quite here, have some other serious issues, but there are commercial companies that are investing in trying to catch up with these technologies. But what we haven't talked about yet is the other approaches that are still in the science discovery phase. And so each of these approaches has some idea to, scale this wall in a different way. So here we have a little turtle trying to climb up over the wall. So each of these is hoping to overcome some roadblock that these others had in some fundamentally different way. Of course, in the process, introducing some fundamentally new problem that we then have to solve, but that's why this is fun. So these are in the basic research stage, and this is sort of where the government research comes in, whereas here there's a lot of private investment. The reason why we have public investment is to do the things that the public companies will not do, and that includes taking basic science problems that are somewhere farther behind and trying to catch them up, with the possibility that they can ultimately solve the issues that the others may not solve, depending on what happens. So we have topological quasiparticles, which you'll hear about at length this morning. There's molecular spins. Defects in semiconductors, such as NV centers. There's cold molecules as opposed to cold atoms. So there's a lot of these other approaches. Okay, and then some of these approaches are starting to look like maybe they'll have different applications. Like photons, of course, are fantastic for quantum communications. It's kind of hard to imagine sending any of these others off at the speed of light, but of course, a photon will do that naturally. Yes.
These cold molecules, are these also net dipole moment zero or something else?
These
Light or
molecules?
neutral atoms?
I think they're neutral from the papers I saw, but there's more papers. There's more papers than I can keep up with. So, yeah. The idea is you go from an atom to a molecule, you have a lot more different states to work with. And so you can find some better, more optimized set of, let's say, 2 hyperfine states that you can play with for your qubit.
Presumably still electric.
The paper I saw was neutral, but I'm not going to say that there isn't another paper that I didn't say that is an ion. Okay. So for example, okay, so photons are of course lend themselves to quantum communications. And then you can think about a hybrid approach. You can do quantum transduction between a photon and something else. So you get the best of both worlds. So you can have your information locally stored in, let's say, a transmon or a cold atom, and then transduce it with a photon, send it over long distances. So even if something doesn't, jump to the top of this race, there are other applications. And then the defects in semiconductors and the molecular spin, so these are molecular magnets, are finding applications as sensors and as single photon emitters. And here, the defects in semiconductors, they came first. With molecules, they're coming now. Like this year, we're seeing the big papers, but they're also, there's a vast array of different molecules out there. And so now we open up the space to find new sensors and photon emitters, which, if they work better, can then come back here and improve our photonic quantum computers. Okay. So, right, so once again, these are all of our different approaches. This one is grayed out because quantum annealing is sort of a different category of things. So I'm going to briefly talk about each one. And here the caveat is I am not an expert on every one. Not sure I'm an expert on any one, but I'm going to attempt to give you an overview. So trapped ions, some people say are in the lead, but of course that's a variable sort of statement that changes with each week. But the idea is that you have an atom. It has various levels. They're hyperfine split, meaning the electrons are interacting with the nucleus. And then they're good qubits because you can cool them down to very close to absolute zero, and you can space them out so they don't talk to each other, and they have really long lifetimes, in the seconds. And then to make them interact, you take a laser and you puff them up to a high Rydberg state. So you excite the electron up to a very high level of the atom. At that point, they change from being nanometer to micron sized, and they interact with each other as they didn't before. So that's your gate. And then you can count them, or you can let them de-excite or de-excite them back down to their original levels. The advantage of an ion as opposed to a neutral atom is it has a charge, so you can use an electron at an electric field to trap it and to move it around. So you can get a many-to-many gate architecture. So you can get any one of your ions to interact with any of your other ions. Of course, the downside is that takes time. They tend to be arranged in linear chains. You have to move them around. Also, the gate operations themselves are kind of slower. So this is targeting megahertz rather than gigahertz operation speed. But they have some, really nice gate fidelities. At least, this is the claim from Quantinium from last month on their archive paper. So, and then if you want to read more about trapped ions, these are some of the papers I found most interesting. There are, of course, many, many papers. Penny Lane tutorial is really nice. So if you want a place to start, I would recommend reading that. Okay. And then this is the Quantinium's latest claim of this 99.843% 2-qubit gate fidelity with, I think this was 50 something qubits, and then this is their architecture. So they're sitting on a racetrack, so you have to move them around, and then you move them into locations where two are sitting in the same trap. And so as they puff up to their high Rydberg states, they interact, and then you get your 2-qubit gate. So, okay, so closely related to that are the neutral atoms, almost the same, except they're not ions, they're atoms. And there's going to be a talk in the school by Kasia, this is her full name, next week. So again, these are laser cooled atoms, and then people are going to molecules. Again, competitive lifetimes somewhere in the seconds, competitive gate fidelities in the 99 point whatever, and pushing up to large number of qubits. But here you can't use an electric field because they're neutral, so you use optical tweezers. So basically lasers that are localizing the atoms into particular locations or arrays. Sorry, Minsung, I stole your parking spot. So, and then once again, if you want to interact them, you pump them up to a high Rydberg state. And then here, because they're held in an optical tweezer, if two are next to each other, they cannot both puff up to the high Rydberg state at the same time. That's prevented. So that gives you like an anti-ferromagnetic gate, to use the analogy of magnetism. So two neighboring atoms cannot be in the same, the one state of the qubit while being pumped up. So that's your 2-qubit gate. And then because you have these laser trapping, you have all kinds of flexible geometries and lattices for how you want to arrange the atoms. So, you know, as a simulator, this is great. You can create all different kinds of lattices. You can create different connectivities up to, I think, 6 nearest neighbors is practical. Okay, this is a sort of advertising slide of some of the Quantum Science Center work. This is collaborations between UC Santa Barbara, Los Alamos, and Inflection, where they're trying to do some basic science with Inflection's systems, and also improve Inflection systems by testing and coming up with some better interface ideas. So, okay. So transmons you've probably heard a lot about in the school. And I also refer you to Sarah, who has been telling me a lot about transmons as well, and we'll be giving a talk next week. So transmons are one of the many different ways you can make a qubit using superconductors.